We will continue looking at the applications in which we do integration in polar coordinates, and this time we'll talk about areas. So previously we learned how, given a curve as, let's say, y equals f of x, and being in the Cartesian coordinate system, we know how to find the area between this curve and the x-axis, or we also know how to find the area between this curve and the y-axis, for example. So if you are interested in finding the area like this, then you definitely should consider having an equation of your curve in the form y equals f of x, even if it is a polar curve. So in polar curves, in polar coordinates, we are not interested in these areas. We're actually interested in a slightly different area. So if we superimpose the polar axis on top of the x-axis here, and pretend like we have a polar coordinate system, the type of area that we're interested in polar coordinates is like this. It's the area of this sector created by connecting the endpoints of that curve with the pole or the origin and the curve itself. So the reason it's called a sector, because in geometry this shape is called a sector. So in polar coordinates we are interested mainly in this sectoral area, and you may ask why, for example, we are interested in such area. And one of the answers is if you recall, one of the Kepler's laws says the following: if you have a trajectory of a planet that rotates around, let's say, the sun in the solar system, then the area spanned by the area of this sector, and let's say t is the time that it takes the object to travel this much, and then let's say in the same amount of t the object will travel this much. As you can imagine, the object doesn't travel at the same speed throughout the entire path, and one of the Kepler's laws says that these areas are the same. But these are nothing but the sectoral areas, and this is why we are interested in computing such areas, and this is what we're going to learn to do when a polar curve is given. So how do we find the area of a sector? So let's assume the following setup. We are in polar coordinates. This is my polar axis. We have a curve which is 1-to-1, so it doesn't overlap here. So that means it doesn't bend this way again, right? So we only have one point of intersection for every ray shooting out of the pole. And let's say this curve is defined by the equation r in terms of theta, And let's say the initial angle here is alpha, and this angle is beta. This is our pole, and this is our polar axis. And I'm not gonna bother you with the development of this formula, but if you open any calculus book, you will find this formula. The area of a sector, like this, can be found with the following integral expression. So the formula is rather simple, so let's go ahead and see an example of how it can be used. So let's consider the following curve, and let's find the area of the sector bounded by the following values of theta. And we're gonna try to envision what's going on here. In this case, we have an equation of a circle. We can draw a full circle here of radius 1, and we want to know the area of this sector. So we're going to go from pi over 6 to pi over 3. So we're looking for this area. And I guess we only need one axis here. So this is the polar axis, this is my origin. And according to the formula, the area of this sector will be equal to the integral from alpha to beta of 1/2 r squared d theta. In our case, the boundaries of the integral are pi over 6, pi over 3. And the formula for r is given. It's 2 cosine theta squared d theta. So to solve this integral, we're going to square the expression in parentheses. So we can get 4 cosine squared. 4 divided by 2 is 2, so 2 can come out of the integral. And we have pi over 6 to pi over 3. And we have cosine squared theta d theta. So this is one of the simple trigonometric integrals, and we can do it by hand using one of the trig identities. And let's see, we know that cosine squared theta minus sine squared theta is equal to cosine of 2 theta, but we can replace sine squared theta with 1 minus cosine squared theta, so we get this identity. And if we add 1 to both sides, we get this identity. And if we take the 2 back inside of the integral, we can replace this integrand with 1 plus cosine of 2 theta d theta. And the integral antiderivative is theta plus 1/2 sine 2 theta, and we plug in pi over 6 and pi over 3. So plugging it in, pi over 3 plus 1/2, what's sine of 2 pi over 3? It's root 3 over 2, so it's root 3 over 4 together, minus we have pi over 6 plus, and sine of pi over 3, it's also root 3 over 2, so it's going to be root 3 over 4, and the final answer is pi over 3 minus pi over 6, which is pi over 6. So we found this area. The area is pi over 6. Let's do another example. Let's consider the following equation. And let's find the area enclosed by one loop of this graph. And first thing we need to do is we need to figure out the boundaries, and in order for us to figure out the boundaries, we have to some sort of imagine the graph of this. And the way I imagine the graph of this, and according to this language involved, so it seems like we're going to have something like a rows, and roses that look like this or something similar. And what would be one loop? One loop is when your r is equal to 0, then it moves and then goes back to r equals to 0. So we just need to find the two consecutive values of theta that make r equal to 0. So let's set r equal to 0, and let's solve this equation. So cosine of 7 theta equals to 0 means 7 theta is equal to, that's going to be plus or minus arc cosine 0 plus 2 pi k. And arc cosine of 0 is cosine of pi over 2 is 0. So we have plus minus pi over 2. And if we divide both sides by 7, then we get pi over 14 plus 2/7 pi k. So we have actually infinitely many solutions, so we can try to write them, a couple of them out, right? But we definitely know that negative pi over 4 is in the solution set, and pi over 4 will be, pi over 14 is also in the solution set, and then we have some others. So the idea is we were looking for two consecutive thetas, and we found them. So this could be our two consecutive thetas. Now, to actually find the area, so this is what we had to do just to find the boundaries. To find the area, we actually have to set up the integral. And we're going to integrate from negative pi over 14 to pi over 14, 1/2 r squared. And luckily r squared is a nice simple function, so we can totally integrate this integral. So we have 1/2, it's going to be 1/7 sine of 7 theta from negative pi over 14 to pi over 14. And we have, I'm going to combine the 1/2 and 1/7, and we have sine of 7 theta, but theta is pi over 14, so we have 7 times pi over 14 minus sine of 7 times negative pi over 14. 7 pi over 14 is pi over 2, sine of pi over 2 is just 1. And sine of negative pi over 2 is just negative 1. So we have 2 over 14, or 1/7. So the area of one loop is exactly 1/7. Next, let's discuss the extension of this idea to something that is very similar in nature to the following formula. If you recall, in Cartesian coordinates, when you had function f and function g on the interval from a to b, this area bounded by the lines x equals a, x equals b, and f and g was could be found using the following formula. It would be the integral from a to b of f of x minus g of x dx. In polar coordinates, we're going to have the following setup. We have a polar curve, and we have two polar axes, and we have two polar curves. One we can refer to as r. Let's say we're going to have two. So here's one, here's the other one. So let's say this is r1, this is r2. So let's say we have two curves, and we are interested in this area, and this angle is alpha and this angle is beta. So can we find such area? The answer is yes. The formula is very similar in spirit to the one we just mentioned on the left side, and it's going to be the integral from alpha to beta of 1/2 r2 squared. So r2 is the biggest one, the furthest away from the pole, minus r1 squared, and all that d theta. So this is how we find this area. So remember, the condition here is that one of the curves has to be always further away from the pole than the other one. And if that condition is not satisfied, so for example, let me draw a picture like this. So you have one curve, and then you have another curve, something like, it's not a good picture. So let's see, we have one curve like this, so, and we're in polar coordinate system, and the other curve just goes very similar like this, right? So we have two curves. Then first of all, the area between the two curves is not well defined, so it could be this one and this one. But notice how the relation between the two curves changes. So if this is r1 and this is r2, then on the interval from, so let's say this is alpha, beta, and let's say we have this other point, let's call it gamma. So notice how on the interval from the end of alpha to the end of gamma, r1 is further away than r2, and on the other interval r2 is further away than r1. So in this case, you cannot use this formula. If you run this formula, it's going to compute something that geometrically is not on this picture. So when something like this happens, what we have to do, we have to find the intersection and apply the formula on each interval separately. So let's see an example of how to find the point of intersection first, and then we'll do an example of finding the actual area. So consider the following two curves. And let's find the intersections. And let's consider the intersections only on the interval from 0 to 2 pi. So to find the intersections, we're going to... So what does it mean for two curves to intersect? That means for the same input, they produce the same output. So in our case, we're going to try to find the values of theta that produce the same output. So to do that, we're going to take one equation, take the other equation, and we're going to set them equal to one another. And that will give us the values of theta that produce the same values of r. So in this case, we have a very simple trigonometric equation. So cosine of theta is equal to 1 over rad 2, or rad 2 over 2. And theta will therefore be equal to plus minus arc cosine of rad 2 over 2 plus 2 pi k. So arc cosine of rad 2 over 2 is just pi over 4. So we technically have infinitely many solutions, but remember, we're only looking on this interval. So we have negative pi over 4, pi over 4, and each one of them we can add 2 pi. So 2 pi to negative pi over 4 is going to be 7 pi over 4. 2 pi to pi over 4 will be 9 pi over 4, and so on. Remember, we're only looking for the values on the interval from 0 to 2 pi. So applying this constraint on this solution set, we get these two values. So the two graphs intersect at pi over 4 and 7 pi over 4. So now that we know how to find the points of intersections, now let's do a problem which requires us to find the area between the two graphs. So let's consider the following example. Let's consider the following two curves. And the question is, find the area that is common to both of these graphs. So find the common area. So in order for us to find the common area, we probably want to understand what the graphs look like. Let's try to sketch these graphs. You can use Desmos if you'd like, but these are relatively simple. So one is r equals 5 is just a circle of radius 5, and r equals 10 sine theta, that's a circle of radius 5 too, but the one centered at 0, 5. So it's going to be this circle. And we need to find the common area. So the common area is this. Now, we will definitely benefit from figuring out these 2 points of intersections. So let's go ahead and do that first. So let's set R1, which is 10 sine theta, equal to R2, which is just 5. So sine theta is equal to 1/2, means one set of solutions is arc sine of 1/2 plus 2 pi k, and the other one will be pi minus arc sine 1/2 plus 2 pi k. So this is just the trigonometry. However, since we have a constraint, right? So let's only consider this situation on the interval from 0 to pi radians. Then we can definitely discard most of these roots, and it appears that this one is pi over 6. We can keep that one, and the next one is 5 pi over 6 plus 2 pi k. So on the interval from pi over 6 right here, right? So this point right here has the coordinates 5 pi over 6, and this one is 5 pi over 6. And now we're gonna find the area. For simplicity, let's label the first curve as R1 and the second one as R2. And it can be very tempting to just write this integral from pi over 6 to 5 pi over 6 of, in this region, the r equals 5 is the outer curve. So to write it like this, 1/2 r2 squared minus r1 squared d theta. As I said, it is very tempting, but it will not give us the right area, because if you zoom in and you look closely into this region, pi over 6 goes here, 5 pi over 6 goes here. So if you find the if you set up this integral, it's not going to return what we want. At least it's not going to return everything that we want. It is going to miss, well, actually it also depends on the behavior. I guess so. I think what I'm thinking is correct here. So this integral will only tell us the area of this green region right there. So you're totally going to miss out. On this red region if this is all you're going to do. So this part of the circle will not be computed by this interval. So here's what we can do to tackle this issue. We can find the green area by setting up this integral. So instead of R2, we're going to put 5. Instead of R1, we're going to put 10 sine theta squared. And again, remember, this is just the green area. And now to find the red area, remember, due to symmetry, those two regions will have the same area. We can set up this integral. Plus 2 integral from 0 to pi over 6. And we only need now to integrate the, this is our R2, this is our R1. R1 will simply be tan sine theta squared d theta. So this is one way to find the area. We're gonna do this integral in a moment, but I was gonna show you another way to set up this integral. Alternatively, what we can do is we can consider the total area of this circle which I shade in blue, and that area is equal to the pi r squared, which is pi, and the radius of that circle is 5, so it's pi r squared. And we can subtract this area. I'm gonna shade it in orange. Now I'm thinking about it, I don't even think this integral that I set up here represents that area. Like this integral right here actually may not be what I think it was. Let's see, so when theta is pi over, I guess I'm not even setting it up correctly, because on this interval, on the interval from pi over 6 to 5 pi over 6, the r1 is actually the external one. So yeah, I don't think that's the right integral to set up. But anyway, so sometimes the most obvious approach is not always the right one. In this case, as I said originally, it was very tempting to just set this up, but it wouldn't do the job. So we have to be careful when we're doing these problems, and we have to again understand the limitations of this formula right here. The R2 has to be the outer curve with respect to R1, and only then it will make sense. So in this case, let's just discard this approach. And let's continue with this approach. So we're gonna find the blue area, which is the area of a circle of radius 5, and we're going to subtract the orange area, and the orange area now is actually the one that can be expressed with this integral. The integral from pi over 6 to 5 pi over 6, but on this interval R1 is the external curve. So we're gonna square it and subtract the internal curve, which is 5 squared, and all that will have 1/2 outside. And this is going to give us the common area. So let's set up this. Let's solve this integral. So we have 25 pi minus 1/2, and we're gonna integrate from pi over 6 to 5 pi over 6. We have 100 sine squared theta minus 25 d theta. We're going to replace the sine squared theta with a double angle identity. So let me recall that identity. We have cosine 2 theta equal to cosine squared theta minus sine squared theta. If we replace cosine squared with 1, minus sine squared theta. Now we have 2 sine squared theta, and sine squared theta can be expressed as 1 minus cosine of 2 theta over 2. So instead of, I can factor out 25 here. So we have 25 pi minus 25 over 2 integral of pi over 6 to 5 pi over 6. And now I have a 4 sine squared theta minus 1 d theta. But instead of 4 sine squared theta, I'm going to write this, right? So, and when you multiply that by 4, 2 is cancelled, so we have 2 minus 2 cosine 2 theta. So 2 minus 2 cosine 2 theta, and we have minus 1 d theta, and minus 1 can be combined with 2, so this is what we have. And let's continue solving this. So antiderivative of 1 is theta, antiderivative of 2 cosine 2 theta is just sine 2 theta, and we evaluate it from pi over 6 to 5 pi over 6. So we get 25 pi minus 25 over 2, and here we have theta as 5 pi over 6 minus sine of 2 theta, so sine of 5 pi over 3 minus, so we're gonna plug in pi over 6 minus sine of pi over 3. So we have 25 pi minus 25 over 2. Now combining 5 pi over 6 minus pi over 6, that's 4 pi over 6, which is 2 pi over 3. And sine of 5 pi over 3, it's going to be, it's in 4th quadrant, so it's negative root 3 over 2. Minus negative sine of pi over 3, so it's going to be plus, what's sine of pi over 3? It's just positive root 3 over 2. So negative root 3 over 2, it's minus negative root 3 over 2, it's the same as positive root 3 over 2, plus root 3 over 2, plus root 3 over 2, it's same as having 2 root 3's over 2, but having 2 root 3's over 2, it's same as having just root 3. And I think we now are ready to write the final answer. We're gonna have 25 pi minus 25 pi over 3. That's 50 pi over 3. And minus 25 root 3 over 2. So this is the final answer. It's not pretty, but it is the area, the common area between those two circles. We can definitely check our work, but in order for us to check our work, we have to plug in this integral into Wolfram alpha. But remember, this integral could have been wrong. So the most important step is setting up these problems and making sure that you don't make a mistake. Once the problem is set up correctly, finding the integral, it's the list of the problems. So once again, in this section we learned how to use integrals to compute the areas in polar coordinates, and the two main formulas that we learned was this one and this one.